Hello, Math 1B in Geometry. I've got a new lesson for you guys. It's an extension from the whole idea of graphing linear equations when you get y by itself. Instead of talking about just what the line looks like with its slope and its y-intercept, we're going to be talking about systems of equations where you can determine the solution where two lines meet by just basically looking at the ordered pair where they intersect. So, you do this by graphing them. So think to ourselves, can we get every single one of these, except the special cases, to look like y equals mx plus b? First one's pretty much done for us. We got y equals 1 over 1x. I'm just assuming there's a 1 in front of that x, plus 2. So to graph that, you'd start at 2 on the y-axis, plot your point, and then you're going to rise 1 unit and run 1 unit because of the up 1, right 1 nature of this fraction. So up 1, right 1, up 1, right 1, up 1, right 1. And you know, I just suggest you do that as many times as you can on a piece of graph paper. You can also go down 1, left 1. All right. Then you graph the line. Handy dandy ruler. Check. Second one. Hopefully we're realizing that if it doesn't look like that, then our graph is going to be all messed up. We need a clean y out front, which means dividing by 3 creates that clean y. Yeah, let's put a 1 in front of that one. So you got y equals 1/3 x. And there wasn't any y-intercept given to us, so you just put a plus 0. And there's our second equation. So we check that first one off the list. The second one starts at 0 and then moves up 1, right 1, 2, 3. Up 1, right 1, 2, 3. Or down 1, left 1, 2, 3. Okay, so if that seemed pretty easy to you, congratulations. You learned everything you needed to for graphing linear equations. Now here's the deal. The solution is not just a visual picture here. The solution is actually what's the x and the y that make this a true statement at the same time that it makes this a true statement. Like if I plugged x in here and y in over here, then the two equations meet. And the answer to that is right there, the place where they intersect. And it should be written in terms of an ordered pair. So in the left spot, the x-coordinate goes there. This is my x-axis. That's how far you have to move left in this case. So move left 1, 2, 3 units. Left 3. So it's going to be -3. And then you move down 1 unit to get that. So -1. There's your solution. Okay, so just showing you what that means. Here are the two original equations. Plug in -3 for x. Plug in -1 for y. Does -1 equal -3 plus 2? Yeah. So it checks out for that equation. Over here, you plug in -3 for x and -1 for y. Does 3 times -1 equal -3? It does. This is the only pair of numbers that makes both of these true. That's what it means to be a solution to two lines, they call it a system of equations, a linear system of equations. All right, let's see if we can do number 2. Wow, fractions. I know fractions are not our favorites, but we can't just keep ignoring them. Our job is to basically get common denominators in order to get y by itself. So the question you have to ask yourself is, what number divides 6, 3, and 2? And the answer to that is 6. So this is going to be something over 6. Well, we already know what it is, 5x. Plus something else over 6 equals something else over 6. And we just got to figure that out by multiplying, in this case, 3 times 2 would give me the middle 6. So multiply the top. 2 times 2 is 4. That y goes into the numerator always. And then right here you would multiply the bottom and top by 3. So 1 times 3 is 3. Once you get that common denominator, I've been preaching it for a while now, ditch the denominators. Now that everybody is speaking the same fraction language, you can get rid of that part of the equation. And now it's a relatively tame piece of information. Can I get y by itself? I think so. Subtract the 5x from both sides. You get negative 5x plus 3. Divide by 4, divide by 4, divide all parts by 4, not just 1 or 2. And you get negative 5/4 x plus, if you take 3 divided by 4 in the calculator, you get 0.75. I kind of think 3/4 is a better way of measuring things because it tells me to start at 3/4 of a block up on the x-axis. So here's a block. Here's half a block. 3/4 is exactly between half and a whole. And now we use the slope to go down 1, 2, 3, 4, 5, right 1, 2, 3, 4. Conversely, go up 1, 2, 3, 4, 5, and left 1, 2, 3, 4. Now it's probably more important to get these out when you do linear systems because we're looking for an actual place where they intersect. So sometimes those weird looking wobbly lines might not cut it. There's our first one. All right, second one. See how we had common denominators over here? They already got them. Ditch the 5s. You're gone. 2x plus 1y equals 3. And hey, since it's just 1y, I can just call it y. Negative 2x plus 3 is our equation. Much easier to graph, much easier to compute than what we had going over here. Start at 3. 1, 2, 3. Now it's negative 2x, so put a negative 2 over a positive 1. So you're going down, down 1, 2, right 1. Or up 1, 2, left 1. Down 2, right 1, down 2, right 1, down 2, right. I think I found the point where it's intersecting. Should be right there on that line. But let's connect the dots just because we're graphing. Okay, we've got the point where they intersect. You'd go from the origin, right 1, 2, 3. I'm looking at this one right here. 1, 2, 3. So right 3, down 1, 2, 3. Why don't you hit pause and try to do this one on your own after I erase the background. All right, so you've tried it on your own. Let's see what you came up with. Subtract 2x from both sides. Divide by 3. There's our first one. Start at 4. 1, 2, 3, 4. Y-axis, x-axis. Down 2. Right 3. Down 2, right 1, 2, 3. Up 2, left 1, 2, 3. Beautiful. Do the same thing here. Oh boy, I see that negative in front of the y and I know it's going to be a problem. I'm going to throw a negative 1 in front just to remind myself that I'm eventually going to have to divide by that negative 1. But not yet. First move is going to be taking that positive 2x, subtracting it so it moves to the other side. So negative 2x plus 4. That negative 1's still in front of the y, so I have to divide it out. Y equals positive 2 over 1 minus 4. So start at negative 4, so below the x-axis 4 units. Up 2, right 1. So up 2, right 1. Up 2, right 1. Up 2. Got it. There it is. That's enough. In fact, I could probably just go that. Yeah, so this point of intersection is right 1, 2, 3. Up 1, 2. Yeah, 3, 2 is the point of intersection. All right, we've pretty much taken care of the concept here. Now, what happens when I throw a special case at you? Well, the question is, do you remember the special cases? One of these lines is horizontal, one's vertical. Horizontal lines, if you recall, look like y equals and then some kind of number. In this case, 4. So that means you would move up 1, 2, 3, 4 units on the y-axis and create a vertical line I just said vertical line. I meant horizontal. So then stands to reason that not y, but x equals a number would be vertical. So vertical lines look like x equals some number. In this case, -3. So that means you go left 3 units and draw a vertical straight up and down line. Here's the point of intersection. to get here, you go left 3 units, up 1, 2, 3, 4. Yeah. Which makes sense, right? X equals -3, y equals 4. Those are the two lines we're graphing, right? What do these coordinates always represent? They represent an x and a y value. So there's a shortcut for you. If you ever see two lines that are kind of like that special case character, you can usually go right to the solution without even needing the graph to tell you where to go. All right, thanks. You guys were a great audience. Thank you very much. Thanks for watching the video. I'll see you next time.